All right, so we're going to review. Let me get adjusting my microphone here. Mr. Microphone. There we go. All right. And so what we're going to do is we're looking at a review of some ideas that we're going to need in Calc 2. And so we're going to walk through kind of the different types of functions we're going to look at. The first type of function that we deal with and is the main focus of an algebra class is a polynomial. And our most general form of a polynomial, and I'll use summation notation, which we'll use, is I have some coefficient, which I have a subscript, which means each one can be different, and the independent variable to a power. And so summation notation says I start with I to the 0 and I work my way across. So if from 0 across, I should say up, by steps of 1. So if n equals 3, I would have a third degree polynomial. And it would be, if we build it up, it would be a to the 0, because we start with I equals 0. And so it would have the 0th coefficient. It could be 4 or 5, whatever holds that place. And then an x to the 0, anything to the 0th power is 1. And so that's our constant. And then we have a sub 1, x to the first power, a sub 2, x squared, and a sub 3, x cubed. And so here we have a third degree polynomial in its most general form. Now we tend to write these in descending order of power. And that's the constant. And these are the coefficients. For each term. And these can take any value as long as a sub 3 does not equal 0, because if a sub 3 was 0, then we'd actually be looking at a second degree polynomial. And so we spent a lot of work on quadratics, because in the quadratic form we have a compact way of stating the answer. Using the quadratic formula. And we could factor and manipulate. In fact, all higher order polynomials can be reduced to a linear term, which would be x minus a equals 0 is linear, or a quadratic term. Any higher order term is some combination of these, which led to the fundamental theorem of algebra that an nth degree polynomial has n roots or solutions including multiplicities, and this is it if we use complex numbers. And we'll come back to this more and more of what solutions are and how they will manifest themselves through the different parts of calculus. But this was the fundamental theorem of algebra, and it focused on polynomials and polynomial roots. But there were some functions that cannot be represented as a polynomial, and they are the transcendentals. And so the main function, the main type of functions that are transcendental are exponentials. And a lot of focus will do with the natural exponential, right? And its inverse, natural log, right, which is the inverse of e. And then in our other transcendentals, which are our trigonometric functions. And I should say all exponentials, so 2 to the x and its inverse log base 2 of x, 10 to the x and its, which is the common log. These are all transcendentals. And then our trigonometric functions, sine of x, cosine of x, tangent of x, cosecant of x, secant of x, and cosine of x. And our hyperbolic functions, sinh of x, cosh of x, tang of x. Right. Each of these has a hyperbolic. Oops, it's cotangent. And if we pay attention in pre-calc, and we will definitely highlight more, there's a link between all of these functions from Euler's identity and De Mornay's theorem, which is e to the x. I'll put an r out in front of it, is equal to cosine of x plus I sine of x. And so exponentials link back to cosines and sines if we have complex numbers. And even more, there are relationships between cosh and sinh directly to e to the x without the imaginary component, and sine and cosine with the imaginary component coming across. And so what I want to set up is that we want to review these concepts to make sure we're comfortable with them. In fact, it was specifically asked of me of where certain trigonometric relationships come from. And I'm actually going to focus on the basic 6 trig functions first in the next video. And then I'm going to look at the hyperbolic and exponentials. Before I move into the trig functions, I want to understand set up the importance of the trig functions. Is we use as one of our main tools the Cartesian plane, where we put our independent variable on the x-axis and our dependent variable on the y-axis. And this helps us define functions and set things across. Now, Descartes did this because if we make things at right angles, they become orthogonal to each other, and so a change in the value of one doesn't change the other unless it's following a function. And these right angles means that any points that we make, any 2 points that we make a subtle right triangle. And we've been using that through Calc 1. When we're making our tangents, we have these right triangles coming up where we have our change in x and our change in y. And we worked on the limiting process with this delta x so that we could get tangents to our curves. And so this triangle hangs in the distance from all points. It gives us our distance formula, where the distance between 2 points is the square root of the change in x squared plus the change in y squared. Now, if I write this as delta x squared plus delta y squared, and I square both sides, this is our good friend, the Pythagorean theorem. So underlying our use of moving things over into using graphs is we're going to use the rules of geometry, specifically the Pythagorean theorem and right triangle rules. And so understanding the right triangle rules and how they pop up are going to be helpful. So like I said, in the next video, I'm going to walk through the trig functions, where the particular values that we kind of memorize come from, and how they work in a geometric sense. And then we're going to look at how they work in a periodic sense, which is an analog. We borrow the geometry and we say, hey, I have some variable here and some variable here. This geometry exists on how I'm mapping them. And that mapping lets us borrow the mathematics from the geometry. Right? My independent variable could be time, and this could be some displacement distance. And this now becomes, the slope becomes a velocity, because the change in distance over the change in time is a velocity. And yet we can still have periodic issues with them due to trig functions coming out. Distance has meaning. We're going to find the first thing we study, area has meaning for functions. So we borrow geometry because we can mathematically calculate things from geometry, and then when we map our things onto this geometric plane, that borrowing gives us a mathematical framework. Alright, so next video I will show you we'll derive the trig functions, and we'll move from there.